So we are now going to establish the very simple rule which can be used to add vectors graphically. And here we're going to look at an example which is two vectors, and they're going to be force vectors, and those are force vectors which apply on a ship which is being towed by two tugboats. So let's draw that example up. Here we have our ship, and this ship is towed by two tugboats, and each of those tugboats is going to exert a force on the ship. We're not going to worry too much about the size of the force. We're not going to specify that. What we're really going to do is look at the principles, and then later on in the examples, we'll actually put numbers into it and you'll see how you calculate it. But really what we want now is for you to master the principles at play. So this ship is being towed by two tugboats. There's the first tugboat, which is a red one, and here it is. And it's exerting a force which we'll call F1. And then there's a second tugboat, which in this case is going to be a blue one, and it's exerting a force which we'll call F2 in this direction over here. So you can see that there is an angle between F1 and F2, and this angle is theta. We're not going to specify it. Remember, we're just looking at the principles which are going to be in play here. And just to make both of these look the same, I'm going to replace that little diagram of a tug there with just the arrow. So now my two force vectors are directed line segments, as we've been doing so far. We want to add F1 and F2 to get a resultant. This resultant would be the direction of the force experienced by this ship, because that ship is going to react to that force. So it's going to accelerate in a particular direction depending on the direction of the resultant. Remember, the resultant is just the sum of the two forces. So it is the result of adding the two forces together. The rule that we use to add vectors graphically, and these forces are vectors, is that we can move any one of the forces so that the head of one force then meets the tail of the other. So I'm going to start off by moving the red force, F1. I could move F1 to this position here, which you can see. So I can move it from there to there. By move, I mean that I change the position of the directed line segment, but I maintain its size and its direction. And you'll see that I've moved F1 from there to there, but it still has got the same size and the same direction. You have to give me a little bit of license because I'm drawing in freehand. I'm not measuring them exactly, but approximately these two are the same size and they've got the same direction. So they're the same vector. Once I've moved F1 so that its tail meets F2's head, I can then complete a triangle, and that triangle will now give me the resultant. And this is the way that I complete the triangle here with a straight line. You see, now I've got a triangle which is F2, the relocated F1, and the longest side is the resultant. If I was to draw this situation away from the physical diagram, then what I'd have is I'd have F2, I'd have F1, and then I'd have the resultant. Notice how I use two arrowheads midway through the resultant to signify it. And I can draw this as a scale diagram using measurements for F1 and F2, and then I can work out what this angle here would be. First of all, I'd work out that angle there, and then I'd work out what this angle there should be, and by measuring the size of that resultant, I'd have a magnitude, and this would be the resultant force acting on the ship. And so all I've done in order to add those two forces, F1 and F2 graphically, is I have taken one of the forces and moved it so that the head of that force meets the tail of the other. I could have moved F2. If I had moved F2, then I would have this situation. F2 could have moved over here. And you'll see very easily that I'll get exactly the same resultant. So it doesn't matter whether I move F1 or I move F2, I get the same resultant. So that is the simple way that we can add two forces using a graphical method.